So, hello everyone. We have today Lucas from Google Brain, and I think you might have like no name like since VIT paper, and he's quite popular on Twitter as well as very active, posts a lot of things. Just to give you a bio about Lucas, so he's from Belgium. He grew up in Belgium with the goal of making video games and their AI, and then probably studied mechanical engineer at RWT at Aachen and further continued PhD in robotics perception. And currently, he's researching representation learning and vision models backbones at Google Brain in Zurich. Yep, I think Lucas, you can start maybe.
Yeah, thanks for the intro and thanks for having me. I first want to mention that this time, since this is a reading group, I wanted to try a new format. So this is not a set of slides with a rehearsed talk, but more like I have the paper open, and I also recently got some like laptop tablet hybrid with a pen. So I want to try, there we go, the pen doesn't write. I want to try like Yannick Kircher style discussion of the paper. And also like I saw that it's supposed to be interactive reading group, so it shouldn't even be just me talking all the time. So I'm gonna discuss and explain the paper, maybe some background behind it, or the reasons why it exists in the first place and so on. But at any time, you should just ask any question. And also feel free to be a little bit adversarial with your questions. Like, don't hesitate to ask, why does this even make sense? Why wouldn't you do that? Or things like this, right? And when you ask a question, you can use this raise hand feature. Then I hear ding, and then I know that I should look for the question. Or if you write it in chat, that's fine too. Yeah, and so I hope you will enjoy this. As I mentioned, this is a relatively new format for me, so I apologize if it ends up not great. And I would also like if you have concrete feedback about this format or how I do this presentation afterwards, I would also be happy to hear that. So then let's get straight to the paper. That paper is called FlexiViT, one model for all patch sizes. Now I cannot do show of hands kind of thing, or does it have the feature? I think not. Yeah. So I wonder how much background you folks have on the VIT model, vision transformer. Now I don't know how to do this exactly. So I'm gonna just say the most important part. But at some point, if I'm losing you in a model description or anything, just feel free again to let me know and say, oh, you would like a little bit more background on like vision transformer or attention or whatever component you think you're missing, right? All right, so let me go back to 1 sec. This one, the vision transformer model itself, that probably most of you have seen, so I'm not going to explain it in a long time, in a long way, but just shortly. What we do with vision transformer is we have input image and output typically classification, at least originally, but then it has been adapted to all kinds of output tasks, right? It's just the regular transformer that I think you all know, at least from natural language processing. So it's just the encoder part even, but we need to transform the image into a bunch of tokens because transformer works on top of a set of tokens, right? And so how we do this is we just cut the image into non-overlapping patches, like a grid, like shown here. And then each patch becomes essentially a token. There's just a linear projection that this patch goes through, and this linear projection is learned. So it's like an embedding, if you want. And then afterwards, we have the patch embeddings that then go through the encoder as tokens. Now let's discuss a little bit more about this linear projection and the patches. They will be the most important part in all of the paper, or all the focus is on that, essentially. So if if the patch size is, let's say, 16 by 16 pixels, then, and the image is RGB, then a patch is 16 by 16 by 3 numbers, which is, I think, 768 numbers. So we can just flatten this as a vector of length 768. And then this linear projection is a matrix multiplication into embedding space of the transformer. If the transformer is like a base model, then this is also 768 is the dimension of this. If the transformer is large, it would be 1024. So this linear projection is essentially a matrix of 768 to, let's say, 1024. And this same matrix is applied on all the patches. And then it's randomly initialized, and then it's learned as part of the whole model learning, right? However, you can also see and formulate this as a special kind of convolution, and this matrix would be the convolution kernel. If you say the convolution has filter size 16 by 16, exactly the patch size, and the stride 16 by 16, so it's actually non-overlapping, it's applied in non-overlapping patches, right? After extracting one patch, it moves exactly the size of a patch to the neighboring and so on. And the output channels count. So output is 1 by 1 pixel then, which is the token, and the channel count of the output is then, let's say, 1024, the model dimension, right? Okay, so there is the, and the rest of the transformer encoder, actually one key thing to notice here, for the rest of the transformer, all of the learnable parameters do not depend on the sequence length, right? I could keep adding more tokens to the input and use all of the same parameters of the transformer encoder. Like the MLPs or feed-forward parts, right? They are just applied on each token separately, so more tokens does not create more parameters there. It's just the same set of parameters applied to the next tokens. And even in the self-attention part, right? All the parameters are token-wise, and then this attention interaction is parameter-free itself, right? So these are the two key parts that will lead to the FlexiViT paper. The whole transformer encoder, all of its learnable parameters, completely do not depend on the sequence length or the number of tokens or number of patches. I use these words more or less interchangeably. Sequence length, number of token, number of patches. Yeah. So far, so good. If I don't hear anything, it means yes. If someone is already confused, then let me know and I try to clear up. Yes.
There is a hand raised.
Oh, I missed it.
I think it was.
I don't see it, and the
Okay.
person raised.
Mike, you
Mike,
had,
I think.
yeah.
Oh,
Sorry,
no.
that was
Okay.
Mike. Sorry.
Yeah.
The thumbs up. Yeah.
I had a question. Hi,
Uh-huh.
Lucas.
Hi.
Yeah. It is you used GLU activation in your
Yeah.
transformer. So was there actually any advantage of using GLU, or you just like saw the idea in BERT where they use GLU and not ReLU? Like, so is there any advantage like that?
Yeah. So for the original transformer paper, that was the whole point, to take the transformer exactly as in BERT, no modification, and apply it to vision. If this works, this was the greatest introduction or like merging of the communities, because hey, you don't even need a single change to adapt it to this whole other community, which is vision. That's why we stuck to GLU. We also did try ReLU, for example, and it made no noticeable difference. I don't know, maybe plus minus 0.5% or something in the end. Nothing that mattered at that point. I know there is now follow-up papers that tune it a lot on ImageNet and so on, and some propose using something else. But yeah, there was no deeper reason than to be ideally exactly the BERT model from language.
Okay, I see. Yeah. Well, thanks. Go ahead.
Okay, so now with these two key parts mentioned or explained, let's jump to FlexiViT. Here the idea is basically, sorry, I want to give one more background. That is that in the original ViT paper, actually, this patch size, we used it quite a lot as a hyperparameter, or in order to create different variants of the vision transformer, right? So we always had this, can I note here? Yeah. So if you look here, we have like 5 different ViT models. And some of them, so the nomenclature is B is base, L is large, and H was huge. And B and L are exactly as the BERT base and BERT large. But what is new and what does not exist in BERT is exactly this patch embedding, right? So we introduced this slash nomenclature to say how large is the patch size. So ViT B32 is ViT base with a patch size of 32 by 32 pixels. ViT B16 is again ViT base, but with patch size of 16 by 16 pixels. What does it mean? It actually has more important, I think, implication on sequence length than on patch size. If the input image is the standard 224 by 224 pixels in both cases, then the ViT B32 will result in 7 by 7, so 49 tokens. So the whole transformer sees 49 tokens, and self-attention and everything works with 49 tokens. If, on the other hand, we use ViT B16, then it results in 14 by 14 tokens, which I cannot do in my head. Let's say, I don't know, 150-ish or so. Is it? I don't know. I'm not good at that. Let's say 150-ish tokens. So the sequence length is a lot more, right? And the whole transformer works with a lot more tokens. So it is a lot slower, but it also has a lot more capacity. And we can see this here. And we also had ViT L32 and ViT L16. And for ViT H, we went down to patch size 14, which added a few more tokens to the sequence length, making it even more powerful. And this is a hyperparameter that is kind of unique to vision transformer as opposed to other transformers in language. And so we tried to cover it to a reasonable extent in the original paper. However, then what we didn't expect at all is that the whole community basically stuck to patch size 16, like all 4 our papers. I think maybe Diet started it, had only patch size 16 models, and then lots of papers were based on that and so on. I think the only paper from not Googlers that I can think of that has ViT B32 released or used is actually the Clip paper. They had a B32 too. But so vast majority of the community kind of ignored the patch size or just say, okay, 16 is the default. We all use 16 all the time. And with FlexiViT, we kind of revisit this and see this unique property of vision transformers as opposed to transformers in general, the patch size, and this fact that changing the patch size changes the sequence length, which does not change the shape of any other learnable parameter except the patch embedding. Can we do more with this? Yeah, I cannot read the whole comment. Yes.
Yasmin, can you unmute and probably ask? Okay, so I will ask maybe on his behalf. So he says choice of patching is interesting, but in language, token as word is fairly obvious. But however, to find equivalent in vision of word would require image segmentation. So that's one question maybe, and also I think the second one is also should optimal patch size depend on the distance of camera position and the size of objects?
Yeah, okay. Yeah, these are good questions. And in some sense, you could say tokenization is maybe like patching in language, right? And we know that tokenization itself is also like there is some optimal tokenization for the task. And you shouldn't compress too much, but not too little either. So yeah, actually, this is also a good point. I think the semantic segmentation community is one that also used the patch size 8 a lot. So that's true. And the second question, optimal patch size, depend on distance of camera position and size of objects. Intuitively, you would think so, but that's ignoring how the model is almost always trained. During the training, we almost always have images with the object of interest to be relatively large, like think of ImageNet or ImageNet 21K or open images, or like any image that people take pictures of usually have reasonably well-centered thing of interest, right? In vision, this is called the photographer bias. Like any images we find that were taken by people have the bias of the thing of interest being more or less central and large enough to recognize. So even in like web data like Lion or something like that, you still have that. But then during training, everybody does quite extreme random crops and quite extreme distortion of aspect ratio and so on, which means that a patch size does not really relate to a specific size of object. Like you cannot really say a patch typically covers the head of a person in the pictures or something like that, just because of these extreme augmentations during training. And so the model is really much more robust to that and can recognize the head of a person, whether it is exactly in the middle of one patch or whether it's cut by between two patches or whether it's much larger than the patch. During training, the model learns to be completely robust to that usually. Okay. All right. So with all of this background, and now let's finally switch to FlexiViT. And I need to turn this. It will be better. No, this is worse. Okay, it's better. All right. So let's see. Yes, the idea here is relatively simple. Given all that I've said, and given the fact that we typically use a changing patch size to get models of different, I should also have said that. So we use patch size a lot, like our group, to get different models on the speed versus accuracy curve. Can you explain the problem in SimpleViT that FlexiViT is fixing? Yeah, I'm going. There was a question. Can you explain the problem in SimpleViT that FlexiViT is fixing? And this is exactly what I'm going to say now. But FlexiViT kind of started as an exploration or question: can we do X? And then it turns out that yes, we can, and that's great. So we use a lot this patch size in order to trade off how strong but slow versus fast but less strong the model is. Like for example, ballpark, you could say VIT B32 is kind of similar to a ResNet 50, both in terms of speed-ish and in terms of performance it gets on typical tasks like ImageNet classification. VIT B16 is actually a lot more powerful and gets much better results, but is also significantly slower. And if you go to VIT B8, this is actually a really, really powerful model, but also pretty damn slow. I don't have the exact comparison model in my mind, but this is an interesting fact, right? They are all VIT based. So all of their transformer encoder parameters are all exactly the same. The only difference is the patch embedding size and the sequence length. So we wanted to see, for the main question behind this is, given this, can we actually learn a single model that works well with all of these different patch sizes or sequence length? So instead of having 3 different models, like VIT B32, you train it, you have it, it's one set of weights. VIT B16, you train it, you have it, it's another set of weights. VIT B8, you train it, you have it, then it's yet another set of weights. Can we train a single VIT B that works with patch size 32, 16, 8, maybe even more? That is the core question behind this paper, and the answer is relatively surprisingly yes. And do you lose anything by doing so? And the answer is actually even more surprisingly, looks like no. And how do you do this? Well, this goes back to all the context I just tried to give. The whole core of the model, the transformer encoder parameters, are all the same no matter what. So it's really only about the patch embeddings. And this, we can in some sense have underlying patch embedding parameter. Remember, it's this matrix of, for example, 768 by 1024. I see a question, I'll get there soon. And so we could have some underlying set of weights that is learned. And then every time we want to use the model, let's say I want to use it as a B16, then I resize these weights in some way that we will discuss later, such that they are just the right size I need for 16 by 16 patch embedding. But I backprop through this resizing. If I want to run the model as a B32, I resize these same weights such that I can use them as a patch embedding for patches of size 32 by 32, and so on and so on. All right, and this resize we backprop through and learn the underlying weights. That is how we can get with the same underlying patch embedding weights, many different patch sizes, and thus many different sequence lengths. And then, as I mentioned, these different sequence lengths, we can just throw them all into the exact same transformer encoder. Nothing parameter-wise depends on sequence length, that just works. Now the question, so does the training also include flexible patch sizes, or is this? Yes, and that's where we're going next. So this was the method. It will become even more clear in the next few minutes. Let's not even look at the results yet, but first, let's first go, okay, on the left side.
So there is a question. Is there any previous work on weight resizing learning through backprop?
Good question. There is, I think, the most related work that I can think of, but it's not about transformers and not in this exact way, comes from a neural architecture search style of paper, which was called the once for all model. And this one trained a mobile net style model where it had a small MLP that transforms an underlying set of filters, like I just mentioned, our underlying set of parameters, transforms these to different filters of different sizes. But it was not just a resize, a whole MLP that learns this and so on. So there is slightly related work on this. Once for All is the name of the paper. It's a really good one. I recommend reading it. Yeah, but not in exactly this way as far as I know, and not in this context of vision transformers patch embedding. If there is, then all of us authors completely missed it, and we are guilty, and you should let us know. Right, let's first look at this picture here, and let's ignore the magic FlexiViT green line, everything is better. Let's just look at the two red lines. These are standard ViT models. No magic, no nothing flexible, just the standard ViT model. That was trained at, one of them as, oh, why I don't have the pen? One of them trained at patch size 16, and one of them trained at patch size 30. So these are two independent models trained independently. After training, we can now take it and we can resize its patch embeddings, right? Think of it literally as just image resize, right? If you look at the patch embedding as a 16 by 16 image or a stack of 16 by 16 images, you can resize each of them. Just like an image, and then you have a filter that has different filter size that's based on this, right? And this is what we do here. This is the x-axis. X-axis is what patch size do we now evaluate this model at, and you can see here. Wait, yes, here. Here, when we evaluate the model at patch size 30. Then this ViT base 30, we evaluate it at its natural patch size, so it gets the best score, its natural score, like something like this. When we evaluate it at different patch sizes, so we resize its finished trained patch embedding and then run evaluation, you can see the performance drops sharply. To the left, the performance is supposed to drop anyways, because the patch size becomes larger, meaning smaller sequence length, meaning less powerful model. But it drops like really brutally, right? Here we have basically half the performance after increasing the patch size a bit. And if we make the patch size smaller, performance also drops, even though it's a slower and a more powerful model. And the same happens with base 16, right? Here. So if we run it at patch size 16, it gets its peak performance. Actually, patch size 15 gets very similar performance, but as we move away, it drops quickly. And with the magic of FlexiViT, which I will show you right after this, you can see that it's change color. Yeah, that it's like a really smooth behavior, right? As I change the patch size, as I make the patches larger, so go more to the left, the performance drops as expected, but really gently, right? Expected because to the left is a weaker model because smaller sequence length. And as I change the patch size to smaller one to the right, so larger sequence length, performance does increase and continue increasing. Now, what is this magic? It's actually super mega simple. Here we have a pseudocode that tries to show this. The non-highlighted code blocks are standard with implementation. And the highlighted things is essentially what needs to change to turn it into a FlexiViT model and FlexiViT training. So here we have the training part, and here we have the model part. Let's quickly look at the training part. What changes? We have this for loop over the mini batches. That is the usual one. But then for each mini batch, we randomly choose which patch size do we want to use for this mini batch. And we really, in most of the paper, we just uniform at random choose one of the patch sizes. And then we run the model with that patch size. And that's it. All the rest is the same as before, like same loss, same everything. Same image size for all of this too. Now, what does it mean run the model at this patch size? That's the bottom part here, the model code. So as we can see, we have this new argument to the model at what patch size should I be running. As I mentioned, this patch embedding parameter, this is a new hyperparameter. What is the size of the underlying patch embedding parameters that are actually trained, which shows 32 by 32 because it's like a nice number roughly in the middle of the patch sizes we want. There is ablation and the appendix that shows as long as you're reasonable, it doesn't matter. If you go too extreme in large or small, things get crap. Then one sec. Yeah, then this underlying parameter gets resized. For now, think of resize really just as image resizing, bilinear interpolation, right? So we resize the, this is too thick line, one sec. Yeah, so we resize these patch embedding weights to the requested patch size that we are requested to run. All right, and this 3 is just the 3 channels input, and D is the model dimension, how many channels output. Okay, and then we use this resized patch embedding for the model. Okay, should probably be here is one of the model parameters. Ignore this for now. I want to first ask, so far so good? Because that is the key, actually. Okay, no hand raised yet. There is one little detail that I completely didn't mention yet because I think it's not important, but now I should mention it for completeness. We have, if I go back to the VIT, I think we have a VIT picture here too, right? Yes. If I go back to the vision transformer, we have this position embedding. Position embedding that gets added to the tokens, right? And the position embedding is a learnable vector, one for each location in the image. Oh, there is a question. Bilinear interpolation is a lossy transformation. I guess you're hoping that the backprop will mitigate that lossy transformation such that the rest of the question I don't need to read. I will get back to this in another 5 minutes. It's a very good question. Notice that I said think of bilinear interpolation. Right, so the one little detail that we need to discuss is the position embeddings. In Vision Transformer, we have these added position embeddings, which are actually just freely learnable vectors, one per patch location. Like here we have one position embedding, here we have one position embedding. So in this case here, where we cut the image into 3x3 patches, so sequence length 9, we have 9 learnable position embeddings. 1, 2, 3, 4, 5, 6. Oops. 7, 8, 9, right? So we have as many position embeddings as we have tokens in our sequence length. How do we do this when we have variable sequence length, as in FlexiViT? Well, this is actually not difficult. We already kind of solved this in the original VIT paper. If you're somewhat familiar with VIT, what we very commonly do is pre-train at some image size, like 2 to 4, for example, and then transfer or fine-tune at larger image size, like 384, which means longer sequence length, in the original VIT paper with the same patch size, which means we need to do something about position embeddings, which we already suggested doing in the original paper, which is essentially just resample more. What does this mean? If you look at again, in the original Vision Transformer paper, we have this plot, which looks at the position embeddings. So each quadrant in this plot is about, I'm really not used to this software, sorry for that. Yeah, each quadrant in this plot, or each square in this plot is one position embedding, and what's shown is the similarity of this position embedding to all other position embeddings. So that's why here the top left corner is actually yellow, so 1, because it's the similarity of this one to itself. Here the bottom left corner is 1, because it's the similarity of this one to itself, and so on. So what we can see essentially here is that the position embeddings, if you lay them out on a grid to what location they correspond in the image, they are really similar. Each position embedding is really similar to its neighbors. So it means they live in high dimensional space, like 768 dimensional, for example, but it's a very smooth space. And if it's a very smooth space, we can actually see the existing position embeddings as support points of some underlying smooth function and just resample more support points from that function, right? We can do essentially interpolation, like linear or cubic or whatever interpolation we want. So let's say we need double as many position embeddings in both X and Y directions, so total 4 times more. Well, we resample intermediate ones by just saying, okay, this position embedding here between those two is really just the average between the two neighbors. This we already did in the original paper for fine-tuning at higher resolution, and it worked really great. So for FlexiViT, we do exactly the same. Back to FlexiViT, we again have to choose a underlying number of position embeddings. We just chose 7 by 7. Again, same story. If you're in a reasonable range, the exact number doesn't matter. If you go completely extreme, it's of course not going to work. So let's say 7 by 7 underlying position embeddings that get learned. So these are 7 by 7 vectors of dimension D, the model dimension. And then we do the same. We resize them. In this case, really, we do bilinear interpolation of them, which is the same we did already in the original VIT, to the number of position embeddings we need. And then we do the usual tokens plus position embeddings are passed to the transformer. And that's the full story with all the details. And we're going to look at the resize next. Why not? There was a question, why not use sinusoidal position embeddings instead of interpolation? There is a difference between vision when you change the sequence length, typically, and the language. In language, when you change the sequence length, it's usually not because you kind of stretch the sentence in some way, but it's because you have a longer sentence that continues. So you want to extrapolate. In vision, typically, when we change the sequence length, both in FlexiViT and in original VIT when doing high resolution fine-tuning, it's actually because we stretch the image. So before increasing or reducing sequence length, the token that was on the bottom right corner of the picture is still on the bottom right corner of the picture. So we don't really want to extrapolate the position embeddings, which is what sine cos would do, but we really do want to interpolate between them because we're kind of adding more details in between the existing ones. I hope that answers the question. It's possible to do it with sinusoidals too, so you wouldn't extrapolate them, but interpolate them. It requires someone to sit down and think it through, and we have the learned ones where we have the working setup, so we didn't really bother looking at sinusoidals more.
Yeah, thank you. I think like Dieter paper introduces sinusoidal embeddings for images, right? Where they normalize the normalize.
Yeah, even before them. I think the first one who did that was actually coming here in Moco V3, which I think came out. Oh, maybe that didn't come out before that. Yeah, it's possible. Yeah, I think it's very natural. And I don't remember if we had the experiment in original ViT paper. Maybe not, but I ran some experiments at some point also showing not too much difference. I think when you have very little data, some hard-coded position embeddings are better than learned one because you don't have enough data to learn what position really means robustly. But yeah.
Okay, thank you.
Yeah. Right, and so if we now train the ViT model in this flexible way, we end up with what we call FlexiViT, and we end up with this green line, the single model that we can run at all these different patch sizes and doesn't fall off dramatically when it's run at different patch sizes, as shown here. So that's the core of the idea and the algorithm and the model and everything, really. The rest is all kinds of experiments, analysis, and things we can do with that. But the resize I promised to talk in detail about. But before jumping to the resize, I want to jump to the coolest result, in my opinion, is we were surprised how good this model is actually, to be honest. And we only noticed that very late in the development. Here we have, this is trained on ImageNet only, so it's not something that only Google can do, like many labs do that, right? So it just showed it doesn't require huge data. And the green curves are all different FlexiViTs. I'll talk about the differences more in a bit. The blue crosses are ResNet 50s. X-axis is speed and y-axis is accuracy on ImageNet. The bottom blue cross is basically your standard vanilla ResNet 50. It's getting 78% roughly on ImageNet. That's the usual, let's say. The higher blue crosses are from a previous paper of us where we use distillation to really push ResNet 50 to its limits. And the top blue cross is actually still now, as far as I know, the best ResNet 50 that exists on ImageNet. And you can see that FlexiViT has multiple variants that are clearly better than that, which is nice. But even more surprising to us was EfficientNet V2, which is one of the top current convolutional models that I know of. I think it's still about as good as ConvNext, which is another top one. Are these red triangles. And so FlexiViT even has variants that are slightly better than EfficientNet V2, or let's call it this the same. And these crosses are Diet V3 model, which was the best previous ViT model. And as you can see, and this will become clear later if I have the time, FlexiViT basically crosses the Diet 3 lines, but then extends the whole range of covered performance. Like here, there's one single FlexiViT, this full line, that is better than all three Diet 3 papers. Not papers, sorry, models that were available, which is the Diet 3 papers is large, base, and small, I think. And here the FlexiViT, also we wanted to see, like all of the experiments in our paper are with FlexiViT based on ViT base. But here we actually ViT base is this one, and this one is ViT small, and then the full line is ViT large. FlexiViT, small, base, and large, just to check that it actually works no matter the encoder size. Like small, base, large, at least they all work. Yeah, so this is a pretty cool, pretty strong result. And now let's talk a bit about Resize, and then let's talk a bit about other things.
Hi,
then...
Lucas, there's a question
Yep.
in the chat. If you can
Oh, I
see.
didn't notice. Sorry. For some reason, I don't hear the ding, so it's fine if you just interrupt me like this with the questions. Does the performance hold good beyond the max and min patch size used during training? That's a good question. During training, there is a short and a longer answer. The short answer is, I don't know. I think we actually didn't try this. But the longer answer is, there is one cool experiment which answers more than the question asks. I promise to still get to it in time, because that's the next coolest experiment. But let's first discuss the resize that was raised as a question before about bilinear interpolation being lossy and so on. So there is two issues. One is that if you have this underlying patch size that you are actually learning, let's say 32 by 32 as we used by default here, then you have this many learnable numbers times input times output channels. And if you resize it to smaller patch size in order to build a stronger model, because it will have larger sequence length, there is loss of information. Like, there is no way around it, right? You're transforming some set of numbers into a smaller set of numbers. If you're going the other way around, you're making a larger patch than the underlying one that you're learning, then there should be no loss of information, ideally. And so we should be able to get the exact same performance at least, right? And we did one experiment early on to try to understand this. So we take a trained regular VIT model. In this case, we take a VIT model with patch size 8 that we trained for some previous work. It's also publicly available. And we evaluate it. At its natural patch size, we get this result on this data set. Then one experiment we can do is to change both the patch size and the image size, right? We can make the patch size 2 times larger, let's say 16, and the image size 2 times larger. No training, no nothing. We take the trained model and do this change and look at what does the prediction look like. If we just do plain bilinear resize, we get this dot here. So it's a complete disaster in terms of performance. But that's not really what we would like, right? We didn't really lose any information, and we didn't really actually change any information. So that means just plain bilinear resize. Yeah, we should have used probably bilinear instead of vanilla, but somehow is not good. And this is the second issue. Why does that happen? I try to briefly explain this. The patch embedding is basically, or is like a convolution, or it's a weighted sum or a matrix multiply, right? If we have an input patch that is, let's say, has the values 1, 2, 3, 1, 1, 1, 2, 2, 2, right? And we have a patch embedding, which has, let's say, 1 input channel, 1 output channel. So let's say just 2, 2, 2, 2, 2, 2, to make it simple, just 2s, okay? Then we do this convolution or product, and we get as a result 1 times 2 plus 2 times 2 plus 3 times 2 plus, and so on, right? This one times this one plus, and so on and so on. Now, what you can see, if you double this one in size and do bilinear interpolation, what you get is actually 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, and so on. And the same story here. But so between the 1 and the 2, you would get like 1, 1.5, 2, and so on, right? And then if you do this sum, you will see that the result of this sum is actually much larger, right? And so it means that after resizing the patch, embedding, and the image, the output of it, the token has much larger magnitude than what was previously there. And so we're giving the transformer a series of tokens which have much larger magnitude than what it has seen before, even though they represent the same pattern. Because if you resize a filter, envision the pattern that it fires on is the same, but the strength that it fires with, like the magnitude of the output, is much larger. And this is the issue. This is why this drop in performance happens. Now, you can come up easily with two different heuristics, which are the next two red lines that perform a lot better, but not perfect. One heuristic is from the example that I showed. You could say, okay, if we double the size here, or we quadruple the size, right? It's double the width, double the height. We should just divide all the numbers by 4, right? And then at least the weights in this weighted sum will end up being the same total weights. And this works a lot better, but is not perfect because this only works in this toy example where there are only positive numbers, for example. And then there is a principled way to do this, which is the green line, which is what we use in most of the model training, which we call PI resize. PI stands for pseudo-inverse. Which is really, I don't want to go to the math now because I also want to go to another cool experiment, but it's basically writing down this desire. We want that after the resize, so that it is as similar as bilinear resize as possible, but after the, or no, sorry, another way to phrase it. We want exactly what we run in this experiment. So we want that the output of using this filter after the resize is as close as possible to the output of using this filter before the resize. And this we can write down as a minimization problem, which we can solve analytically with using pseudo-inverse. It sounds fancier than it is. And then at the end of the day, it's like some numpy call somewhere to generate this PI resize matrix. You know, if you do bilinear resizing, you can implement it as multiplying by a matrix that actually we have the picture. And doing this PI resize is just multiplying by a different matrix. Here is an example picture, actually. Bilinear resizing can be implemented as just multiplying by this matrix here on the left. For resizing down, I think, and resizing up by this matrix. And PI resize would be multiplying by this matrix or that matrix, and how it's derived is this analytical formula. You do it once at the beginning of training. It's like a not even iterative thing, just a few numpy functions. We have open sourced the code, so you can look at it. Bottom line is you shouldn't be scared. And that's it. And so it means multiplying the underlying weights that you learn, this 32 by 32, by this matrix before giving them to conv. And that's it. Yeah. And this is one part of the answer. So if you have a pre-trained model that you want to use, then definitely use PI resize for changing the patch size. If, however, you are training from scratch, then it almost doesn't matter. Then exactly what the person who asked the question, do we hope that backprop will mitigate this? That's exactly true. You can train from scratch with just regular bilinear resize and it works basically the same. If you train from scratch, here we try many different ideas of resize. Blue is actually plain resize and green is PI resize, and they perform essentially the same. Yeah, so the whole advantage of PI resize is that it works really well with pre-trained models. And now I'm almost out of time. Wow. There is a lot of more experiments, but maybe two key things, or 2 or 3 key things I would like to mention. Okay, I just want to briefly mention that we as a group often have gotten criticism that, okay, everything you do is really just image classification. How do I know it works for like segmentation, detection, and so on, more structured output tasks where maybe image resolution matters and so on. So in this paper, we took this feedback to heart, and we have panoptic segmentation results, we have zero-shot detection results, we have image text results, we have semantic segmentation results, and the story is the same across all of these. The story meaning that whenever you train, let's say you train a VIT B30 and a VIT B16 for your task separately, or you train a FlexiViT and then run it as 30 or run it as 16, you get the same performance, meaning there is essentially no loss in accuracy by doing FlexiViT instead of training individual models for the individual sizes. So that's the takeaway, and that it's really simple to implement. So we can do FlexiViT, like pre-train a VIT model in FlexiViT way, and then use it in all of these different types of tasks. Or we can what we call flexify all of these kinds of tasks. So take, for example, our VIT code base, which is our detection code base, and add this randomization in that training code base, and then just train this detector with the in the flexible way, and basically both work. And one cool result, which now goes to what I promised to get to, the question about going beyond max and min patch size, which is not directly the answer to the question, but I think very cool and very related, is what we can do is pre-train, so we call it fast transfer, is during pre-training, pre-train a FlexiViT. But then when we transfer it to the data set of interest, transfer it only at a small patch size. The interesting thing is, or at a fixed patch size, I wanted to say, sorry. The interesting thing is it remains flexible. This experiment can be seen here, or in this experiment where we take the FlexiViT that we pre-trained on ImageNet, the large one, ImageNet 21K, and then we transfer it to the standard ImageNet. This is nowadays a standard setup in Vision. But when we transfer it to standard ImageNet, we transfer it only at a single fixed patch size. So essentially, we treat it like a regular VIT during transfer. And if we transfer it with this grid size, only here where we see this dot, or grid size is a sequence length synonym. And then after transfer, evaluate it at these different grid sizes, we get all of these like points on this curve. If we fine-tune it at this patch size or grid size, and then after the fine-tuning, run it at all of the different patch sizes, we get this curve. And they are all roughly the same, and they are all much better than what happens with a regular VIT, not pre-trained as a FlexiViT, which is the red one here, which really is good only around the grid size that it was transferred at. Meaning, we can pre-train FlexiViT in flexible way. We can do the transfer with a very large patch size or small grid size, which is very cheap because large patch size means fast and small model, but then still get the benefit of, after transferring it, running it with smaller patch size or larger sequence length and having improved accuracy. So that's a pretty cool feature this, for example, allows. And then, of course, you can go, and we didn't do that yet, it's just too much work, but you can go and think of advantages that it may have in mobile deployment, for example, right? Maybe you just need to deploy one set of weights, but you can run it at different speeds depending on how much battery you have left or whatnot on the same device, instead of needing to deploy many different set of weights and switching between them and whatnot. Yeah, and then there is many more experiments, but I should stop now. And I hope you got the core idea.
So I had a question on when you fine tune this on a fixed patch size,
Mhm.
Then why do you like don't see a performance drop on others? Intuitively, it seems that probably it should optimize to a certain patch size, right? Like as
Yeah.
AIT pre-trained from scratch. Then why do we see that phenomenon? Is it because like maybe some emerging abilities out of this pre-trained model, and there's a zero-shot transfer?
Yeah, so this is not zero-shot transfer. This is actually fine-tuning all the model parameters. But usually fine-tuning doesn't go super far from the original model, right? Usually, and what we do here too, in fine-tuning, you use a smaller learning rate than you used in pre-training, for example, and the model you start with is really good, so it gets a low loss very quickly, and low loss means it doesn't continue learning or doesn't need to change much more. I think it relies on that. I should also mention this result is from ImageNet 21K to ImageNet 1K. So you may say, okay, but these are very similar data sets. Maybe that's why we have the same on other classification data sets too. Yeah.
I see.
There's a question by Harsha. Harsha, you
Yeah,
can
Harish. Yeah,
open
Harish.
your mic or you can just.
Yeah, thank you for the talk. I actually had two questions. I don't know if the second would be fine, but like I'll go with the first one. Do you think like this phenomenon of like being able to use the PI inverse to use it, plug it into a VIT and do it, is this do the fact that there's some part of the VIT which is already learned to deal with this, and we're trying to identify it by fine tuning or using this method? Or is it like a function of the training methodology that has been implied? Like, I hope that makes sense as a question.
I didn't fully understand the question.
In the sense that, is this like if you take a normal VIT, do you think, like, I think similar to what Jay said, is it like an emergent behavior, or like as a function of the training we have this sort of
This figure here was created with a normal VIT. No flexi, nothing, no PI during training or anything. So PI resize is a nice way to load some weights of a regular VIT from some patch size into another patch size without destroying it too much. But note that here we also change the image size accordingly, right? Such that the meaning is still the same. So this is more of a understanding experiment than a practical recommendation experiment. If you want the VIT to do something meaningful when changing the sequence length, then you need to do this during training, which is the main figure here, right? If you don't do it during training, then it doesn't do too meaningfully, which is the two red curves.
And I had another question that's probably related to the original vision transformer. It's been a question for a while, so I'll just quickly ask. Like, with regard to the class token that generally is prepended, right? Is there any theory or any study that sort of understands how exactly it helps? Like, I think there's an accuracy gap that comes in, and like given that when you fine tune it on a new data set, say you've done it on ImageNet and you bring in Cypher 10, like it kind of like it's different. Like it's 1,000 classes and then 10 classes. So just trying to understand, has there been any study or theory of why that class token helps, so to speak?
Okay, the first answer or first part of the answer is the same as about the GELU question. Why is it there in the first place? Is because we wanted this to be exactly like BERT, but in Vision. And BERT has this, so we added it. Already in the original paper, though, in the appendix, we showed that it doesn't matter much. We can also not have it, but global average pooling, for example. And for classification, which is all that we did then, it's the exact same results, but you need to tune, I think you need a different learning rate or something like that. So I think for classification, it doesn't matter much. There have been some papers looking at it and comparing to global average pooling, what happens in the model and so on. For other tasks than classification, I think it may matter more, but I actually don't really know. I think it's just cool to bring this idea into the field of vision, that this exists, like this class token, like that's something else than global average pooling exists basically. And for example, the first diet paper did a cool thing, right? They had the class token and the distillation token as 2 extra tokens, which you will never really think of if you're stuck with global average pooling. So yeah, I don't think we have 100% clear understanding. I don't think, at least for classification, I don't think it matters too much, but it allows some cool new ideas.
Thank you so much. Yeah.
Oh, I also forgot to mention, but we open source the code, and also the models are open source, like these from the main figure are open sourced on GitHub.
Anyone has any questions?
Okay, then I will go get dinner now.
Yes,
All right. Yeah, thanks for having me.
Yeah, it was really nice presentation, like basically going through the paper and actually explaining more like inner parts and like, yeah, much more, I
Yep.
think, better than probably like the slides. I think, yeah, but yeah.
Yeah, I would also like to hear feedback. So if any of you have like thoughts about this type of presentation or what went well, what didn't, just shoot me an email. I will be thankful for that. All right, then bye-bye.
Yeah, bye, Lucas. Thank you for the talk.